the main memory, which does the carrying of, because either the CPU either need data or instructions, right? If you need the instructions, it gets it. No, it gets instructions, sorry, and then feeds the memory back with data, right? Because it gets instructions from,
The main memory that's around.
yeah, that's the RAM,
Okay.
right? So it gets instructions from the memory, decodes them, does the process and everything, sends back the data to the RAM to keep, like the output, whatever after the
Yeah.
processing. Are we there? Mm? That's you want to say something?
Yeah, now I want to ask a question.
Yeah.
Okay, so you're saying that there is one bus is shared that's carrying both instructions and data between the CPU and the main memory. But we have three buses. We have one for data, we have the other for address, and the other one for controls.
Yeah.
Yeah. So which of these is how am I going to put the question?
Okay. Is it at every point, like from data side, is the data divided into two? Or the control
Yes,
side,
is
is
the
the control
control
divided into
divided into
two?
two?
Yeah.
No, no, no,
No.
not really
No.
that. How how do I put the question?
Something. Let me see.
Okay. Uh, what you're saying is that between the main memory, that's the RAM, and the CPU, there is a
Yeah.
bus.
Yes.
Okay, which bus is between? Because it's supposed to be three. One
Mm,
transferring data, the other one transferring the address, the location now where information is stored, and the
wait.
other one
Yeah,
um,
yeah. I get you. I get
transferring
you.
control.
Wait, let me see. Let me share my entire screen here so that these guys can see. And do like a research, right? So you guys can see. Let me see. Window. No entire screen.
Okay, mic is muted.
Oh, thank you for seeing that. Okay. All right. So let me see. Oh, okay. Okay. So I want to see if I can get a diagram, right? So I can actually see
See the
that.
volume.
Yeah. One Newman. I can popular. I just type board and it's
No,
everywhere.
that
Okay. Mm, actually, one which actually describes the bosses guide. It's more CPU stuff.
I think you have to precisely be your prompt.
Let's see with bosses.
Yeah.
Please. Okay. Let me see this one. Address, data, control. So this one is for address. This one is for data.
Data.
This one is for control. But like we were saying, what they say, we said in Vonuma, one
Was
bus is shared,
shared.
carrying both instructions and data between CPU, which means let's come back here. It means this one, like we said, it has control stuff, right? And inside this one is one way. This one is one way. But this one is what? One, two.
Okay, so you're saying that the data bus is
Get
like a bi-directional bus.
exactly.
Okay.
Get instructions,
Okay.
and then the other way around now is the data from those after the
Processing
processing.
of the instruction.
Exactly.
Okay. Oh yeah, yeah,
Okay.
yeah.
We get it. Right. I hope that's clear.
Yeah, it's clear.
All right. Okay. Let's
So that means
continue.
that the
It really
address
makes
bus
sense.
and the control bus are
Just one. Yeah,
unidirectional.
unidirectional.
Yes, unidirectional. Yeah.
Yeah, it really makes sense because one data is a big thing.
Exactly. All right. That's clear. Hope we're all okay. Yeah, cool. All right. Okay. Instruction execution. Okay. Yeah. Fetch, decode, execute. Fetch, decode, execute. That's how they call it, the CPU works, right? So this is the heart of how computers work. So step one, fetch. So PC holds address of instruction. Instruction fetch from the memory into IR. So what the IR was like. Let me see again. Is it instruction register,
The
which does
instruction
what?
register
It holds
holds
current
current
instructions,
instructions.
right? Hmm? So let's think of program counter instruction, because now we're going to make use of all of this right now to actually see how the CPU works with them. Hmm? Yeah. Okay. Memory address register, memory data register, accumulator, and the rest. Okay. All right. So PC holds address of instruction fetch from memory and is put into the
Instruction
instruction
register.
register. Thank you. Then PC increment. What's PC again?
Program counter.
Exactly. So program counter increments, right? Like the next instruction, right? Or is it the next
The
instruction?
next instruction.
Exactly. Okay. Then now we'll go to step two to decode, right? Because remember, we have put those instructions inside the instruction
Instruction
register,
register.
right? Now we have to decode it. In fact, we have to finish with this guy right before going out to the next instruction,
Mm.
right? Yeah. So control unit interprets the instruction and knows that okay, it determines the next action or the required action. So like you have to interpret it and know that okay, this guy is what you do, this guy is what you do, right? That's a decoding process, just those two. Then step three now has to actually execute it. So Allo performs computation or operations based on the decoding, right? Know that okay, this is what Allo will do. Then results stored in register or memory. That's clear, right? The cycle repeats millions or billions of times per second, depending on the stuff we are doing. I mean, just keeps going, just keeps going, just keeps going. The von Neumann bottleneck, I mean, obviously, it must have its own. Yeah. So a bottleneck is a component or process that limits the overall performance of the system, like a narrow bottle restricting water flow. Okay. What is it? So CPU and memory share a single data pathway, obviously. You already see some kind of issues with that, right? I mean, I think that's why you kept bringing it to. But somehow you like, I mean, why? You could just make another one that does the thing, right? But let's see. Instructions and data cannot be transferred simultaneously. Obviously, since that she's using one pathway, it means when we are getting instruction, we cannot be sending data.
Okay.
That's clear, right? Okay, results. CPU
A
often.
question. So what happens with the data bus? Okay, one goes and the other comes.
One,
Okay,
yes,
okay.
there are
Okay,
two.
yeah, they cannot.
Yeah. So CPU, so results, as a result of that, CPU often waits for memory, which limits performance. Hmm. Like all these data must go first before now I get my instruction to continue. Hmm. Yeah, and based on how much data to is also determine the speed too. I mean, it's very fast, obviously for us, but
No, like if you're using like an 8 RAM machine, like very very slow.
yeah, yeah. But I'm just like for us humans, right? It's very fast. But for the guys, like I'm actually waiting for you. So
Is
another
that the same philosophy like when your device freezes? Like for example,
because
might be maybe you
what
click and
what
then you have to wait
what can
before you
cause your
have like
device to freeze? Or when your device freezes, most of the time they'll be like maybe close tabs, close
no, I'm
softwares that are
okay.
open.
Let's not say freezing. Like for example, when you're using like a very slow device. Like let me see for example, I'm using a machine
Takes longer
and
to
it takes
do.
long like yes, maybe I click on Microsoft Word and then it takes like I have to go and drink water then come back.
Come back, yeah, like takes a
Before
very
it
long
opens.
time.
Is that the same? Is that the philosophy?
Yeah, yeah. I mean, you always said you're working with a slow machine, right? You always tell that me the RAM is slow, and so if the RAM is slow, registers might not be the best too. And also, in fact, it might not be talking about the registers. They say it's even slow to get it from the
Information.
information, right? Like it's normally even slow to even get. The Maya house to also be to load the data because maybe the instructions generally should be faster. Like getting information should be generally faster than sending data back, right? So you can imagine. So yeah, it's someone the
It's
same
really
thing.
very slow to get the information.
Yeah,
Um,
to send it
to
now.
send it out.
Yeah. Mm. So analogy, they say one lane bridge with traffic going both ways. Yeah, yeah, so, yeah. That's it, right? If that's why you see some bridges it's like okay, it's just directional. This will
Some
have
people that are going this way want to enter the other road
exactly.
that
There's no path in the middle to separate those two guys. And everybody wants to just enter their own side and stuff
Has
like that.
has this solution not already been solved?
Yeah, it should be
this is the for new man was 1945 now,
1945.
so our updated pieces normally this thing
Has well, let's say it comes with
the evolution.
yeah ways to solve this or to reduce the effect because most of the archives still use the von Neumann stuff, but now you have
Maybe an
maybe
upgraded from new man
different
architecture.
exactly. Yeah, you hear things like threads, you hear things like um like instead of you like some people so you get some people actually you get you get things like calls when you go to buy a machine, you get things like calls,
Okay,
you get
like
things like
iPhone
threads.
one,
Yes,
sound.
yes, and
Okay,
all of those
Core
different
iPad.
things. So those are different ways to actually mitigate this kind of things.
okay,
You get it? Yeah. How modern computers okay
okay.
mitigate the bottleneck? Yeah. Even though they still use the von Neumann principles, yeah, but the principle is still there. I mean, it's cool, it's elegant. You can really see that it's working, right? Yeah. Even if you are not putting, just explaining to someone, the person can actually
Yeah,
see it working.
the rest is fine.
Yeah. So we have what? Cache memory, L1, L2, L3. So aside from registers, we have other memories now, which means that the CPU must not go and store data right at the memory again. Could just
Data.
store them in these cache
Cache.
memories. Are we there?
Making it faster.
Making it faster. So we have instruction pipelining. Maybe we are going to let me see, is it there? Let's just keep that. Instruction pipeline to do recession. Yeah. And they look straightforward, but do more research on it to see what it actually does. Prefetching as well. I think let's do research on all of these techniques here. Yeah. Cache
Okay, so
memory,
sorry, catch me.
yeah, cache memory, instruction pipelining, prefetching, parallel execution, multiple calls. You see the calls I was talking about. It's a good thing for you guys to know that I mean when getting your laptops and stuff like that, I mean you can actually understand why people emphasize on stuff like this. Maybe a lay person who just uses it for movie watching and stuff. You don't really need it, right? But now you guys are going to be carrying out a lot of processes on your laptop. You see, so you need to know all of these things. Know why this laptop is best fit for what I'm doing. Okay, shall I continue? All right. So these reduce but don't eliminate the bottleneck, obviously, right? But at least it reduces it. Yeah. They'll be like, why did I just put one boss there again to do the thing?
Mm,
I don't know why you because because over here it clearly states that the issue is because there's one boss doing two things. So why don't they just add one other
like
boss?
one for data, one for instructions.
Not
Exactly.
sure for that, yeah.
Maybe I don't do the research you should get that.
This
I don't
life.
know, is it that the bus is expensive or what?
Maybe there's no space. So it can be two buses.
Okay, von Neumann versus Harvard architecture. So yeah, there are other architectures out there, obviously. I mean, it's always that one person will just do one thing and everybody just agrees, right? Another person will be like, no, mine too has to be there. So instruction and data memory. So features, right? Instruction and data memory. So von Neumann has
Yeah, like this guy is separate.
Yeah, which
yeah,
makes it better.
exactly.
Just
So
like
what are
when
we
you say,
using for Newman?
uh,
Is there a
Or,
reason?
or see this, or we'll get to this. If it doesn't
the
answer
Von
a question,
Neumann and the Harvard, which came up later on. The Harvard came after Von Neumann.
Harvard should come after.
So it means maybe Harvard now was trying to work on the bottlenecks of the Von Neumann
Exactly.
architecture.
So then bosses see shared separate.
Safe way,
Speed, slower,
slow, faster.
faster.
You mean
Com-
in terms of complexity?
Yeah, in
complexity,
terms of complexity.
simple
Actually,
and more complex. And more complex means more resources, more
yeah,
this to actually build it right. Yeah.
and maybe to even understand it too, not just to be able to understand
Exactly, because we as programmers should be able to understand the systems we're working with. Yeah. Most modern, yeah, you were saying something else. Uh, I
He
already
was
know.
named after somebody. Yeah, maybe it could be
it
named
could be
after.
a research that was done in
it. In
Harvard
Harvard
itself,
University.
right? So yeah. Then von Neumann was maybe his own that he did privately. Yeah. Most modern CPUs use the modified Harvard architecture. So it's like if you say it's modified, it means that but Newman came first and there was yeah, exactly. Which blends the simplicity of the von Neumann architecture, unified main memory for data slash instruction with Harvard's speed using separate instruction L cache and data D cache caches inside the CPU for fast simultaneous access while still relying on a single bus to main RAM for flexibility and cost effectiveness. So it means like I just mix everything for like to really get the better, like I said, better
A blend of
flexibility. More,
two.
yeah, a blend of two. Exactly. Yeah. Because the fact that one is simple obviously has its advantages.
Yeah.
Yeah. So additional resources, yeah, additional resources over here. So you can always you get to them. I'll see if we don't get this stuff to Iceland maybe by tomorrow. I'm going to send you guys the links to these resources so you can visit them. Right? Yeah. On the Discord channel. You guys are on Discord, right? Yeah. So exercises, we have exercises here. Um, what is the stored program concept? Why are registers faster than RAM? What does the ALU do?
Is it for us now
To answer
or
all that
So
assignments?
I'm
assignment.
just going to let me see. Okay, I've read all of that. Now let's start answering. So what is the stored program concept?
Stop program concept. For the Von Neumann architecture.
Yeah, obviously. I mean, the whole of this topic is von Neumann architecture, right? So I mean, you just have to trace back what's von Neumann all about,
Yeah.
and storage. We're talking about stored. What stores programs? And that's how I'm answering the question. Really.
I think the stored program concept is that instructions and data should be stored in memory.
Exactly. Yeah. Because like we saw in the like we started right that things were supposed where programs were being rewired. Like if you want to change a program, you have to taking the wire here, all of those kind of things. Why? Because instructions and data were not stored simultaneously in one place. But von Neumann came out with the fact that you store them both in memory. Yeah. Then why are registers faster than the RAM? Registers, Tina, no hear your voice. I hear your voice now, Tina. Why are registers faster than RAM? You know what registers are, right? You know what the RAM is. Okay. So why do you think they are faster? I mean, just have to provide something, right? Whether wrong or correct, we just want something, some addition from you. So registers are found. Where are they found? Where are registers found? With respect to the CPU, where are registers found? Or let me see, where's the
Respect to the
whiteboard?
CPU.
Yeah.
Where are they from?
The speed is very little now.
So we have a CPU here. Well, where will the registers be found? So this might see you. So where are registers found? So registers are found within the CPU, right? Where is the memory found? Memory is found outside the CPU. So why then is it faster to use the registers? Or why then should registers be faster than the CPU than the memory? Sorry, is smaller,
Easily
obviously,
accessible.
easily
Since
accessible.
it's already in the CPU.
Exactly. Yeah, that's clear, right? Like,
Source information is short.
yeah, exactly.
Okay, that's when we use the example of you bring your bag.
Perhaps yeah, the whole house and the
Yes.
whole thing.
Yeah, that's how we use the example. Yeah. Okay. Then what does the ALU do?
And it does use um, arithmetic calculations.
Okay, yeah. So that's arithmetic logic unit, right? Those arithmetic operations, logical operations, what else? Comparison operations, right? And all those math stuff. Yeah. Okay, true or false? So I'm just going to read all, then I'm going to start now. You guys answer. So instructions are stored separately from data. I'll talk about the von Neumann architecture. Hmm? Yes. So say somebody answer and tell me he was thinking about the Harvard architecture. Then the control unit performs calculations. The bottleneck is caused by shared buses. Okay, let's start. Instructions are, this one is for Lanye. Instructions are stored separately from data. True or false?
False.
Okay, yeah,
Yeah.
because that was the program.
Program.
Uh,
But that's the whole essence
That
of
was
the
the whole
volume.
yeah, yeah, exactly.
and the problem too.
And the problem.
Yes, yes. This one is for Louise. The control unit performs calculations. That's true. That's true. It doesn't perform calculations. Um, this one is for Asang. The bottleneck is caused by shared buses.
Bottleneck caused by shared.
Shared buses. The
Yeah.
bottleneck that is experienced in the
Yeah.
von Neumann architecture, right?
Yeah.
Yeah, due to the fact that they have to share that data bus. Yeah. Okay. Exercise 2. Hmm? Oh, we'll start from zero. That was a good one. All right. Um, execution cycle. Explain what happens when executing
Wow.
add a comma B.
When adding,
Yes. No, when
No,
executing
no.
that,
When
I'm
you're
not saying
executing, you're supposed to
yes.
explain what happened.
Let's say that's the instruction, right?
The whole process.
Yes.
Yeah, that's the instruction which the CPU, let's say the CPU went to that address and got that instruction. So how would the CPU execute that? So I also want to explain that process.
mm,
I mean, your own way, right, must not be the same way. I mean, you can see design and architecture you are explaining to us.
Ah,
I mean, is that at the end of the day, you get the result of A plus B. Mm? Yeah.
okay. I think that what happens is we have the program counter gets the instruction at first, and then maybe stores it.
They can even go to that fetch the codes.
Yes.
Yeah,
Some
so
can
get those
exactly.
Yes.
because remember those counters the main problem
Yeah.
now.
I
So
think it's
step
yeah.
one is fetch. Yeah.
Yeah. So I think the program counter holds the address of the instruction at
Yeah, of that particular instruction
okay
itself that we're talking.
yes, and then the instruction is fetched now from memory. So the instruction register fetches the instruction acts from memory, and then the program counter now.
Yeah, continue. Yeah, increments.
And then increments. Or do we get A and B first?
correcting me.
Right?
Right.
You're actually correct yourself now
You're
because
Yeah.
correcting
Okay,
yourself.
okay, okay.
Yeah.
So
You do get-
you
okay,
cannot add if you don't really
If you
have
don't-
the
if you don't have the-
stuff that you have to add, right?
So
Yeah.
the PC holds at, then IR holds A, then the PC now has D. I think.
Okay. So
The program counter has at the instruction at, then the instruction register. The first, I don't want to say variable,
Okay.
but
no,
the
but the
first,
program counter holds with the address first now, or gives tells the instruction register where to go and get
So
the
So at the
instruction.
point, I think after the program counter holds the address of the instructions, it has already gotten the address. I think the next thing now is getting the variables.
think like you should store the variables, right? So store A, you store B, right? And then now before you can add
Uh,
A and B. So the CPU should be able to get A, right? Keep it somewhere, right? Get B, keep it somewhere, and then get the instruction to say add A and B, right? Mm. Then you know that okay, then it decodes that mean that add A and B as okay. Keep A now, like tell the alone now that okay, you have A in this register, you have B in this register, add them.
okay, means you're saying the program counter holds A and D, then the instruction register now accesses A first, and then the PC increments B to A.
Yes, yes, yes,
but
yes.
after the program counter holds the address of instruction, is A and B an
The
instruction?
the instructions are found in IR, right? Add A and B is the instruction.
Okay,
Add A and add A comma B, right? Or depending on how the instruction is, right? That's the instruction to do it. You get it? Which means A the problem already in that instruction. You get it? That's what I'm just trying to say. It means A should have already been fetched, right?
But can you explain it like using this count like the counters?
I think this counter is missing something from its explanation now.
What does program counter do, first of all? If you know what a program counter does.
Holds addresses of the next instruction.
So it just holds addresses.
Of
It
the
knows.
next
So
instruction.
at this moment, it holds the address. The next instruction is for that add A and B, right?
Mhm.
So he knows that okay, he goes and fetches like one of the those buses, right? He goes and fetches that add A and B
What's adding the bosses?
and stores it.
I feel
No,
like
you must add A the buses, Gab. Yeah, go ahead.
I feel like at itself is not like an address. It's just
No,
A
I-
and D. A and B are like memory locations.
I think the variables.
Yes,
I think A
variables
and B.
are locations
I
and
yeah,
memory locations.
exactly.
Okay,
So the
yeah,
program
yeah.
counter holds A and B as those addresses. So now the instruction register now accesses A as the current one. Then the next one now, which is B now, is the next instruction. It now takes it A and B. So we're not actually considering add maybe as an address. The only addresses that we're considering is A and B. If I'm understanding the program counter everything.
Yeah, that's another of well. Let's put it this way, because if we go back to the question, right? It says that what? Where is it?
So
Okay, explain what happens when executing this. This is the instruction. This instruction is in a particular slot in memory, right? Inside this slot, we just have add a comma b,
Mhm.
right? You get it.
Yeah.
Obviously, a comma b is like another memory address somewhere. Are we there? Hmm?
Yeah.
So when the PC holds the address of this next instruction.
Instruction. Which is
You get it? So it comes
Mm,
and
okay.
gets it. Are we there?
yes.
And based on that, it knows that what the next thing should obviously be that word. Maybe I should fetch A, I should fetch B.
Okay.
You get it? It fetches it, and then adds them and sends the data back, and it stores the values in another location, like they are the result of that addition. Are we there? So it also depends on how, like I said, it also depends on how the computer will see it, like because some CPUs are also programmed differently, right? Another one could be that okay, I've already fetched A and B are actually already in the registers in the CPU. But right now I'm thinking that A and B are still there. We don't have A and B, right? So it gets that add A and B. It sees that oh I don't have A, I don't have B. But I see that because obviously like I said, A and B are like memory locations, right? So it goes to the memory location of A and gets A. Goes to the memory location of B and gets B and then adds it, and then sends now the data to the memory and stores it or whatever the person wants to do with that data, right? If the calculator to display it, is that
So we're saying add AB is an
it's the
is the
instruction that you
instruction that
yeah
has
yeah
an
that
address on its own.
yes
Okay.
yes.
This is an asset. It has been 33 for a long time. I don't know if it's still recording.
Where is that?
The little pop.
No, that's Gamali.
Ah, okay.
Yeah, it's really at
So wait,
33.
these online people, they have to be in class from 8 a.m. to that supposed 4 p.m. Jesus Christ, sitting on your PC.
I think that's
let's
why they also send the notes now.
let's continue please.
I never do that.
So we have design thinking.
No, you skipped.
Bottleneck.
Oh,
Me.
bottleneck analysis. Oh, sorry. Why does increasing CPU speed alone not improve performance? Why do they not just focus on increasing the speed at which the CPU goes and fetches the data from memory?
Even if it goes and fetches data from memory, they'll still use one part to pass in. At the end of the day, it will cause more chaos
At the
instead.
end of it, that delay is still there, no matter how much the speed is, right?
Yeah.
That delay is still there.
Data instructions in the system,
Because it's like you're leaving the root cause and
trying to solve
trying to
something.
solve some
Yeah.
other thing, which is not actually the problem, yeah, or the main problem. Yeah.
Just like saying in our roads, if you don't widen the instead of widening our roads, you instead tend to increase the speed of
Of the
vehicle
car.
of the cars.
Yeah.
So you
You
cause
know, cause more problems.
yeah,
Yeah,
more
yeah,
problems actually.
that's a good way of saying it. How about all in the same line? Does anyone have any other insight to this?
That's promotion is really nice.
Yeah, yeah, yeah. It's- Okay, design thinking. How would separate instruction and data buses help performance? Obviously, it does.
So I think it's going to go with performance first because since he said seven bosses, why one is giving instruction, same instruction, the other one is listening back.
Exactly. Yeah, you must not wait that.
Yes.
Why might this increase hardware complexity?
Because now you need two buses, which means you have to increase on maybe um, wiring.
Oh
And the
yeah,
connection between those two buses and the other parts.
yeah.
That's
Um,
another thing to say
And
gets
what also I just see like wire. Maybe it's not actually wiring,
It's not
right?
actually, yeah.
There's a little lot
Yeah.
there.
I mean, just adding a button to your keyboard is really something.
Exactly.
Really huge.
Yes. Yes.
So,
That's
really
it.
complicated.
Okay, this one is research task, so you guys can just write that down. Okay, that's a good one. Those are good.
So how do we submit assignments?
Ooh, like, well, the ISLM platform is there for that, but see, we have these lectures there, like before you guys start submitting there.
Okay, so from now till we have the lectures in room. So this assignment is for us.
Well,
This is more like research now.
this research, right?
Not
Which
really
means I can
assignment.
come next class and say, "How was your research? What did you do?" You understand? Mm.
Our next class will still be joined.
No, don't think so. Well, till finish this module, it's going to be joined.
We have
So
one, two,
there's
three.
no there's no guarantee we're going to finish the module now, right?
Oh, okay.
No, and I'm going to end.
So now,
No, this actually this one finishes five today. This five is not the end of this module.
we'll finish this
Okay.
5 today.
Okay, operating systems. Let me see. Okay, I thought there's nothing there. Oh, there's a link to Gigs for Geeks. Uh, what was it? Let me go there.
But I just delete.
All right.
Okay.
Come again. Let me see how long it is.
It's not long. It's not long. All those other things I just
All right, let's continue. Let's continue. At least let's get about your coding system. I mean, I've actually already gotten
Yeah,
about
this
your
is about
coding, so this one is more of a reminder, even. Yeah, we need to do more of the work. We have to go into those links and actually research what
but
is
just once there.
inside. Okay, let's continue. So, an operating system is
You not check on those online if they have questions. Please. Those online.
oh,
But maybe it's the
Let me
things
see.
at the comment section or something.
nah, there's actually no one online. So we're just recording the stuff.
Okay, okay.
Yeah, so that they can have it after too. Yeah. I think
Jesus.
one
So
of them came and started coming and going but all right, let's continue. What was time? I mean, I gave a break last time, 5 minutes. So
No, even in the break where it's asking questions. So I've not really had break for
Break,
that.
break, yeah.
okay, okay. What's time even?
It's 12.
12. Oh, let's take a little pause. Let's see. We'll start at 11. 11:30 and
It's
12:30. Sorry, my
So
I want to see that
actually,
it's
my
really
laptop
stuck
is
at home.
yeah. Even though this is my laptop, it's like 1 hour backwards. That's why. Okay, let me pause my. That was a good one. Okay, let me just leave. Because if I'm here, I will still be asking you guys questions. Oh, And this also goes for everyone. There's a bathroom
Please,
that's behind this door.
okay. Education.
My specimen. Poisonous experiment.
Yeah, it's your good.
Yeah.
So this class need to be more for the first. You guys said you just put me for introduction.
Introduction.
Uh-huh.
Introduction.
My pattern is sleepy. I just came this morning from Bangladesh.
Where? Bamenda.
This morning.
Oh,
I just kept my bags. I put my bag on my phone.
shit.
That's not an excuse. That one aside.
I understand. I understand. No. Oh, Asha. That's what I can say. I mean, like so, we have other stuff there, right? But at the moment, most of the stuff be a revision since that first chapter which we had, right? Just get across everything, which means we're going to speed up. Except you guys have more questions. Because what has actually been keeping us is whether we discuss and all this before moving to the next one. Yeah. Let me tell you how I want to start. Yeah. That's this one.
This next 8 months will be the longest months of my life. To go. 12 minutes break.
Okay. Where is okay. All right. So operating system tutorial. So I've always what our operating system is obviously. I've seen what it does. Now this particular one gives more detailed overview, but I'm just going to go through. Like I'm not going to click these links that are here, right? That'll be for you guys. I mean, your research after this, right? Yeah. Like I'm just going to. I mean, I'm going to go through that stuff. I'm just going to mention them, and obviously, you guys will be like, "How does it do this? How does it do this?" So now I'll leave that for you guys to go and click the link, see what it actually does. All right. So an operating system is system software that manages the hardware and software resources of a computer. It acts as an interface between the user and the machine or and the parts which you can touch, like the hardware. Yeah. Enabling smooth execution of programs and efficient use of the system resources. So and the system with of system resources among running applications. So we know that okay, the CPU can do this. We know that the memory can do this. We know that the storage, the hard disk drive can do this. But on their own, all of that cannot be done. So they need something to tell you that, oh, store this data here, or this one is for storage, this one is for processing, this one is for this one is for the memory, this one is for, you get it, right? Mm? It's just like um, the calculator will do can do all of those things, but you keep it down there. It's just there, right? Without you coming to actually do something with it, will not do anything, right? So it's just the same like a CPU. The manufacturer has put all the machines and everything to actually make it do its job well, but without the operating system, it won't do that job. Are we there? Key features: manages computer resources such as CPU, memory, and files. Acts as an interface between user and hardware. Performs core functions like process, memory, and file management. Organizes system resources similar to different departments in a government. Yeah. Examples include Linux, Unix, there's another one called Unix, Windows 11, MS-DOS, Android, Mac OS, and iOS.
Phones, like
Yeah,
Apple products are better for computers.
yeah,
Like, so is that the question? For this Unix, I thought that Unix, Linux, and Mac came from Unix.
like you said, came from.
I mean, like it's different.
Yeah, yeah, it's different. You can see because an operating system is a whole unit, right, which offers all of these different stuff. Are we there? The operating system at its core we have the kernel. You get it? Before other stuff. So when we say it came from Unix, like okay, maybe they just took the Unix core, then they built upon and actually came out with their own stuff. You get it? Yeah.
Okay.
So Unix is normally standalone stuff on its own. You get it? Before now, those other Linux, Mac OS, and the rest.
And is Unix still in operation?
I don't think so. Yeah. I don't think so. Yeah. Because actually, you hardly even see it in examples of these systems. Maybe I'm always surprised seeing it in gigs for gigs. Yeah. I mean, okay. Why do we need an operating? Any other question? Okay. Why do we need an operating system? So to manage hardware resources efficiently, efficiently, to run multiple programs simultaneously. So without it knowing, like without it knowing that okay, this is the architecture of this machine, it means that okay, he has 8 cores, he has this, he has this. It means that I can run this one here, run this one here, run this one here. Your computer doesn't just put everything anywhere and in fact you need a good like an operating system to actually tell it to know how to do all of those, right? I mean, you just go, yeah, it's 8 core and all this kind of stuff, but you need something to tell you that how to use those things. You get it? Mm? Yeah. Because how can I put it? Uh, what's a way of putting it? Mm. Okay, maybe we can talk about bottles. Not really bottles, because normal everyone knows that bottles was to put something